All right, looks like we're good to go. Hello again. Today we're going to talk about section 2-3 regarding functions. Several of the objectives today include the difference between what a relation and a function is, domain and range, determining whether relations are functions, function notation, and increasing, decreasing, and constant functions. So a relation, any set of ordered pairs is a relation. A function is a special relation in which for each distinct value of the first component of the ordered pairs, there's exactly one value in the second component. So a relation can be any set of ordered pairs. It could be a graph, whether it's a line, a circle, a parabola, an ellipse, anything that I can draw on a graph, that is a relation. Function is very specific, and we'll talk more about that as we move on. So, definition of function says for each member of the first part of an ordered pair, there's only one y value that goes with it. So, in the case of f, notice I have x values of 1, -2, and 3. It doesn't repeat. And since the x value does not repeat, there's no way that it has a different y value that goes with it. So there's no repeating of the x values here. So this is a function. Function g, or relation g, relation g. Notice I have an x term of 1 that corresponds to 1, but I also have an x value of 1 that corresponds to 2, and I also have an x value of 1 that corresponds to 3, and then I have a x value of 2. So because I have a singular first item 1 that's paired with 3 different, which is actually obviously more than 1, this is not a function. Relation H. I look at my x values. This -4 pairs to 1. This -2 pairs to 1 also. And that's okay that 1 repeats on the y value, or the second term. But then I have another first term of -2. I have another x value of -2 there, and it's paired with 0. So right here I have two different y values, or two different second values paired with that first value of -2. So because of that, this is not a function. But again, all three, f, g, and h, these are relations. A function is just a very specific relation such that each x value, or each first number, is only paired with one other number. Domain and range. For every relation consisting of a set of ordered pairs x, y, there are two important sets of elements. The set of values of the independent variable x is the domain. So some key things here to look at is when you see independent, we are talking about x. We are talking about the domain. We are talking about the x values. We are talking about the horizontal axis. The horizontal axis is independent. The first variable in a ordered pair, that is your domain. The set of all values of the dependent variable is y, and that is the range. So dependent is the y values. Dependent is the y-axis. So even if we're not using x and y, dependent, range, we're still talking about your vertical axis here. It says finding domain and range of a relation. Give the domain and range of each relation. Tell whether the relation defines a function. Okay, so on part A, let's talk about the domain. Nice. Okay, the domain. So the domain is the set of the x values. The domain is the first number of an ordered pair. The domain is the horizontal or the y-axis. And so the domain of this function, we're looking at the first values. We're talking about this 3, this 4, but it repeats, and this 6. Okay, so the domain. When you're listing a domain or a range, you want to put these in order from small to large. So on the x-axis, think about reading from left to right. As we read from left to right, smallest to largest. So the domain is the set of numbers. So I'll put a brace here indicating a set. The set of numbers containing 3. That's my smallest x value. My next smallest value is 4. Now notice that the 4 is repeated twice in my relation here. If I tell you once that 4 is a part of the domain, I don't have to tell you again. And in fact, if you tell me more than once, then that's not quite right. So when you're telling me a domain or a range, each number is only listed one time. So there's by 3, then 4. My next smallest x value is 6. And those 3 numbers right there, that is the entire domain. Now let's look at the range. So the range is the second value. And again, we want to put these in order. So my range consists of a -1, a 2, a 5, and an 8. So each of my range members, each of my y values is only repeated one time. So I don't have to worry about writing it down multiple times, and you never would anyway. So I'm just going to write down those in order from smallest to large. Range, again, we're talking about the y-axis, the vertical axis, and we're going to start from bottom to top. We always go from small to large. So the smallest number here is -1, then 2, then 5, and then 8. And that's the range. And then, so the instructions up here say give the domain and the range of each relation, then tell whether the relation defines a function. And so again, when we look at these two middle terms right here, we have two different domain values, two different x values, that one of them maps to 2 and one of them maps to 5. So we can't have an x value of 4 that goes to both 2 and 5, so this is not a function. Okay, so part B, give the domain and the range. So this is another way of representing data. So in part A, they represent data as a set of ordered pairs. In part B, we're looking at data, and this is actually referred to as a mapping. The first oval, 4, 6, 7, and -3, those are my x values, and those map to 100, 200, and 300. So 4 goes to 100, 6 goes to 200, 7 goes to 200, and -3 goes to 300. And so that 4, 100 right there at the top, that represents the coordinate or the point for 100. And so a mapping is just another way of displaying data. And so the nice thing about a mapping is that if a data value is repeated, they actually don't write it down twice. You'll just see multiple arrows. In this case, you'll notice on the y's values, the 200 there, that one is repeated, but that's a y value that's repeated, so that's okay. On the x side, if you notice, there is nothing that's repeated. The 4, the 6, the 7, and the -3 only map to one number. And so because they only map to one number, this is going to be a function. But let's go ahead and discuss the domain of this function. Again, the domain is the set of values, the first set of values. Okay, so in the case of this problem, it's 4, 6, 7, and -3. But when we list our domain, we will write those in order from smallest to largest. So the domain is -4, 6, and 7. Our range, that's going to be, what those numbers map to, and the range happens to be my other side. So my range is the set of numbers containing 100, 200, and 300. So that is my domain and my range. And then is this a function? Well, the x does not repeat, so yes, this is a function. Part C. Part C gives us yet a third way of displaying relations, and this is the form of a table. You might have heard it in the past referred to as a T-table because it looks like a T in the middle here, and we have our independent variable on the left side and the dependent variable y on the right side. And in our table, we do have all of the points in this relation listed out. And if you'll notice, my x values are on the left side there. So my x values consist of -5, 0, and 5. So my domain is the set of numbers from small to large, -5, 0, and 5. My range, the range is the set of y values, set of dependent variables. In this case, there's only one number that's repeated over and over and over. So the range of this data is 2. Again, we do not repeat. And once it's listed as a part of the domain of the range once, we know it's there, so we don't say it again. And this data, the x values, each x value has its own y value. Even though it's the same y value, that's okay. The point is the -5 only goes to 2, the 0 only goes to 2, the 5 only goes to 2. So this is in fact a function. So recall on it for a function, x cannot repeat. The first value cannot repeat. The second value can. Find the domains of the range from graphs. So on the previous slide, we looked at relations in 3 different formats. We looked at them as a set of ordered pairs, we looked at them as a mapping, and we looked at them as a T-table or a table for short. The fourth way to look at data is to look at it on a graph. And so here you see 4 graphs, and we are going to just give the domain and the range of each of these. Okay, so let's start with the domain on part A. If you'll notice in part A, we have 4 distinct points. I just have 4 points. So because I only have 4 points, I can get the domain, the exact range from those 4 points. So the domain. Remember, the domain is the set of x values. And so that's the first number in an ordered pair. And going from small to large, our smallest one, again, we're talking about the x-axis. We're talking about horizontal, so we'll read from left to right. So as we walk across this graph, if you will, the very first x value we come to is -1. And as we keep increasing, we get to 0. Keep increasing, we get to 1. Keep increasing, we get to 4. So the domain of this data is -1, 0, 1, and 4. Now for the range, we want to go from smallest to largest, just like we did on the x's, going from smallest to largest. On the y values for range, we go from smallest to largest. So starting way down low and moving our way up, we finally get to a value when we're working our way up right here at this point. And so -3 is going to be the first member of my range. Continue to move up. My next value is -1. Continue to move up. My next value is 1. And continue to move up. My last value is 2. And so that is the domain and the range of graph A. So again, graph A is simply 4 distinct points, meaning I can list every individual x value in the domain. I can list every individual y value in the range. Okay, let's look at part B. So part B is a little bit different here. Now we have this oval, and you'll notice on this oval it goes on the x values, it goes from -4 to +4, and the y values, it goes from -6 to 6. But folks, there are infinitely many points on this oval. It is impossible to list every single point on this oval. So what we're going to do is we're going to list the domain and the range. We're going to write it down as an interval. Okay? So let's start with the domain. Let me undo that. I need to go back to my pen. Sorry about that. So domain. And this graph kind of has it written out for you. It says that the domain is everything between that vertical line and that vertical line. And so it's like I was talking about on graph A. If we're moving from -infinity, moving along the x-axis, I don't touch that graph until I get to -4. The instant I get to -4, I'm touching that graph. And though the graph is going up down here and down around here, you'll notice that everywhere in between -4 and +4, that graph exists. And as soon as I get to +4, as soon as I pass that +4, I'm no longer on the graph. So the domain consists of every number between -4 and 4. And you can't list them all. You can't say, well, it's just -4, -3. No, 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 no. Because there are so many points between -4 and -3, like, I don't know, -3.9. How about -3.999? -3.9999, -3.9876. So you can see there is no way to list every number of the domain going from -4 to +4. So the domain, we're not going to write it in this notation over here. Instead, we're going to write the interval. The domain includes every number from -4 to +4. Now, can it be -4? Well, absolutely. When you're looking at graphs like this, we're going to assume that the intent is for the graph to actually touch -4 and go to +4. And so because it can be included, we're going to enclose this -4 and +4 with a set of brackets. So when you put a bracket in, you're indicating that yes, it can equal that amount. It can equal -4. It can equal +4. And of course, it's going to equal everything in between, because this is read, the domain is the interval from -4 to +4, and that is also including those endpoints. Okay, let's look at the range now. So we're going to have the same discussion about the range, but now we're talking about going from the y-axis all the way down, all the way up. So if we're way down here, I'm not at graph B yet, but as I move my way up, I finally touch the graph at -6. And as I move my way up from -6, I'm still on the graph, I'm still on the graph, I'm still on the graph, and the instant I pass +6, I'm off the graph. So the y values of the range consist of every number between -6 and 6, and there's no way to list them all. And so again, from small to large, the range goes from -6. Range goes from -6 to 6. Can it equal -6? Yes. Can it equal +6? Yes. So because it can equal those endpoints, we put brackets on there. All right, part C. Part C, I want you to notice there's arrows on that. We have, and this line has a negative slope, it looks like. This line is decreasing forever. But what I want you to notice is the fact there's arrows on here. There's arrows on both ends. So though the line is going up at an angle like that, if you think about it, it's always going to the right. And it's going down over here, but not only is it going down over here, but it's always going to the right. So it's always going to the left and the right, which means it goes to the left forever. It goes to the right forever. There is no beginning point. There is no ending point. It is impossible to list every single x value that's on that line. So it goes from How far to the left? The smallest number ever? Well, it goes on to negative infinity. And since it's going to the right forever, it's going to positive infinity. Now, if you go back to part B, we knew the exact value of the domain. It started at -4. It ended at +4. So because we knew those exact values, we used brackets. Well, in the case of infinity, folks, there's no way that you can tell me the exact value of infinity. It just indicates that it goes on forever. And since we do not know the exact value of where this thing stops or where this thing begins, we do not use brackets. You will never put a bracket on an infinity sign, but instead, infinity signs will always use parentheses. So this thing goes to the left forever, negative infinity. It goes to the right forever, positive infinity, and it contains every number in between. Range, same conversation. The range of this data to the right, it's going down forever. To the left, it's going up forever. So since it goes up forever and down forever, the smallest value is going to be negative infinity, value positive infinity. And again, since we don't know exactly the value of infinity, we will use parentheses. So the range is every number, goes down forever, negative infinity, goes up forever, positive infinity, and everything in between. Part D. Part D is a little different. If you'll notice, Part D it's a U-shaped graph. This is called a parabola. And this graph, though it gets steeper and steeper and steeper as it goes up to the right and as it goes up to the left, it's always moving more to the right. It's always moving more to the left. And so the domain of this function is actually going to be the same as part C. It takes forever to get there because it's moving slower and slower and slower to the right and slower and slower and slower to the left as it increases. But still, x goes to the right and to the left forever. So for graph D, the domain is negative infinity to infinity. And again, because we don't know the exact value of infinity, we're going to use parentheses to close those off. Now let's talk about the range. Range on this one's a little different, because this graph is not going forever. In fact, it's got a minimum. It only goes down to -3. It never gets below that point. So if you're talking about the range, again, we always talk from small to large. From down here, the graph doesn't exist. But as we move up, we finally get to the graph at -3. And as we go up, we never get off of the graph again. So this graph, I guess my hand made it disappear. Okay, so the range. This graph started, the lowest value, it started at -3. And then it goes up and up and up and up, and it goes up forever. Since it goes up forever without bound, we don't know where it ends. It goes up all the way to infinity. Okay, so let's look at, talking about brackets and parentheses on this interval. This interval started at -3. It started exactly at -3. Not -3.1, not -2.999. It started exactly at -3. And that is going to be an assumption we use on these graphs. It appears that it's -3, so we're going to go with it. We have no reason to say it does not go to the -3. So can it equal -3? The answer is yes. And so because it can equal -3, we're going to use a bracket. Now I'm going to write this bracket a little different this time and talk about the bracket. So when you use a bracket, when you use a parenthesis. A bracket is used when you know it can equal. Okay, so this graph can equal -3. And if you think about a bracket, if I was to draw the top part and the bottom part of the bracket first, there's the top part of the bracket and there's the bottom part of the bracket. The bracket has a built-in equal sign. Okay, so when you see a bracket, think equals. So can this graph equal -3? Yes. So because it can equal -3, we know the exact value of -3. We're going to put a bracket on this side. And then on the other side, we have infinity. And again, no one knows where that is. So we put a parenthesis on the range. So the range of graph D is including -3 up to infinity. Agreement on domain. Unless specified otherwise, the domain of a relation is assumed to be all real numbers that reproduce real numbers when substituted for the independent variable. So what this is saying, when you're looking at a function and you're asked to determine the domain of a function, you will start with thinking to yourself, okay, the domain is all real numbers. And then from there, you start looking at, are there any exceptions? Okay, so all relations will start with the domain of all real numbers. Vertical line test. Vertical line test is used on a graph to determine if it's a function or not. The vertical line test is if I take a vertical line and cross it across a graph, if that vertical line only touches the graph one time in any place, then it is in fact a function. If at any time going across the graph it touches more than once, it is not a function. And we'll look at some examples of those in just a moment. Okay, use the vertical line test to determine if the relation is a function. All right. There we go. Okay, so these are the same graphs we looked at a while ago. All we talked about a while ago was the domain and range of these, and so now we're going to look at, are these functions or are they not functions? And so what we'll do is we're going to do a vertical line test. And so the vertical line test tells us that if I take a vertical line, and I'm going to just try to make a vertical line as good as possible there, and then let's take this vertical line. Okay, it doesn't want me to take it. That's fine. I'll just use my pencil and whatever. If I was to envision a vertical line going across line A, a graph A, it only touches that point once. It only touches that point once. It only touches there once. And those are the only 4 points. So at no point does a vertical line touch 2 points at the same time. So this passes the vertical line test. And that's written as VLT, vertical line test. So that is a function. Okay. Part B, if I was to take a vertical line, say right here, notice that vertical line touches the graph at 2 different points. So if this happens any given time, this happens one time on a graph, then this is not a function. So this fails the vertical line test. Not a function. Part C, take a vertical line. It doesn't matter where you draw a vertical line on this thing. Okay, no matter where I draw a vertical line, it only touches the graph once. It passes the vertical line test. It is a function. And D. This is a parabola, and it doesn't matter where I draw vertical lines. It only touches the parabola one time. It passes the vertical line test. It is a function. Decide whether each relation defines y as a function of x and give the domain. So again, we're given 5 different relations here, and as we start these, we assume that each relation is in fact a function. And so letter A, What is the domain? Well, the domain is the set of x values. And so for y equals x plus 4, what values of x can I plug into this? Well, I can plug anything in. You give me any number, I don't care what it is, and I bet you I can add 4 to it. So because you can give me any number that I can add 4 to, there's nothing weird going on in this thing. The domain of this function is, in fact, all real numbers. So the domain is going to go from negative infinity to positive infinity. So it's the interval negative infinity to positive infinity. Range. Well, this looks like y equals mx plus b. This is just a line. This is a line with a y-intercept of 4 and a slope of 1. So it's a line that kind of looks like that. So it's going up forever to the right. It's going down forever to the left. It's just a line. The range is all real numbers, negative infinity to infinity. So, and since it's a line, this is a function. Okay. Part B. So what can x be? Well, can x be anything? So remember, for x to work, if I plug an x in, I have to get a real number back out. And here I'm taking the square root. So I don't know if you remember, there's a problem with square roots. And the problem is the fact that if I was to take the square root of any negative number, say negative 1, that's not real. Okay? And so I cannot take, in the real numbers, I cannot take the square root of a negative number. So I do have restrictions on what my x value can be. And so this is going to be the case anytime you see a square root. So if I'm taking the square root of something, or we'll talk about that later on. If I'm taking the square root of something, I know that whatever I'm taking the square root of, in this case 2x minus 1, 2x minus 1 has to be greater than or equal to 0. Because if 2x minus 1 was negative, that means I need to take the square root of a negative number. And we can't do that. And so setting 2x minus 1 to be greater than or equal to 0 is going to help me determine what my domain is. And so to solve this for x, I'm going to add 1 to both sides. So 2x is greater than or equal to 1. Divide both sides by 2. X is greater than or equal to 1/2. So x can be anything as long as it's greater than or equal to 1/2. So the domain, and I'm sorry I switched to green. In the past I've been using green to represent range, but this will separate problem A from B. There you go. So the domain. So the smallest possible x value is 1/2. I can enter any number that I want bigger than 1/2, but I can only go down to 1/2. So the domain is the interval from, and it can be 1/2, so I have a bracket. The smallest possible value for the domain is 1/2, and it can be as big as I want. So it goes up forever and ever and ever and ever and ever, so infinity, and we use a parenthesis around infinity. Well, what about the range? Well, the range, I don't know if you remember what a square root function looks like, but a square root function, the parent function, looks like that. And so if that's what a parent function looks like, this one's been kind of manipulated as far as the x has been multiplied by 2, and then from that value subtracted 1. But it's still going to look like that when I graph it. And so because I know that's what it looks like, I know this has a minimum value at the smallest x value. So if I was to plug in that 1/2, 2 times, let me go ahead and change colors. 2 times 1/2 minus 1. 2 times 1/2 is 1. 1 minus 1 is 0, and the square root of 0 is 0. And so this graph does in fact start with the smallest possible y value of 0. So the range it includes 0 because it can equal 0. It goes from 0 to, and just as I showed you up above, it's going to be going up and to the right forever like that. So it's going to be going up forever, so infinity. And so there is your range. And that is a function. Okay, part C. Y squared equals x. So this is saying that x equals y squared. So if we think about that, can x be anything? Can y be anything? In the case of this problem, if we just start thinking about different values, let's see, if I put in an x value of, x can't be negative. So why did I just say that? Why did I just say x can't be negative? Because x is equal to y squared. And if you take any number, I don't care what y value you give me any y value you want, positive, negative, it doesn't matter what it is. You give me a y value and I can square it. Okay? And so because of that, we can kind of start this one backwards. Y can be anything. So because y can be anything, my range is from negative infinity to infinity. But what can x be? Well, the smallest possible number that you square, 0. If you square 0, you get 0. You square 1, you get 1. You square negative 1, you also get 1. So the very smallest possible value of x is going to be 0, and then it goes up from there. So the domain goes from 0, 0 to infinity. So is it a function? Well, let's think of some values. How can I get, say, 16? What number can I square to get 16? Well, if I squared a 4, I would get 16, because 4 times 4 is 16, but there's another one. Remember, a negative times a negative is positive, so 16 negative 4 is also a point on this graph. So I've just shown you two different y values for the same x values, so by definition this is not a function. Part D. Y is less than or equal to x minus 1. By definition, y is a function of x if every value of x leads to exactly one value of y. And if we substitute particular values of x into the inequality, we can get a lot of different answers. X could be anything. I don't care what number you give me for x. I can subtract 1 from it. And so the domain is all real numbers. So negative infinity to infinity, which is the same thing as saying all real numbers. And the range happens to be the same thing, negative infinity to infinity, which is the same thing, all real numbers. As far as this being a function, it's not a function. This is an inequality. To give you an idea what this graph was to look like, I'm just going to do a quick sketch of what it would look like. If I was to graph the line y equals x minus 1, it's going to have a slope of positive 1 to the y value of negative 1 like this. So there's the line, but it says less than or equal to, so I'm talking about everything down here. And so you'll notice that if all of this area is shaded, then there's no way that I could pass a vertical line test through it. So this is not a function. This is an inequality graph. Okay, part E. I'm going to work part E, but before I do so, I'm going to go ahead and clear the screen. So if you're doing screenshots or whatever, you can pause the screen and do so. Let me go ahead and clear this, and then we'll work part E. Okay, part E. Remember, a relation. Initially, when you look at some kind of a relation, you start off by assuming that the domain is all real values. And so if you refer back to part B, and I'll write that again, the square root of a negative number is not real. So anytime you're taking the square root, if you're taking the square root of something that's negative, it's not real, so you have to eliminate that from the domain. So that's why in part B we change the domain from all real numbers to x is greater than or equal to 1/2. In part E, let's start the same thing. Okay, x can be anything. The domain is all real, but then we start looking at, hey, there's the denominator. And I can divide by negative numbers, I can divide by positive numbers, but I cannot divide by 0. A little glitchy on the board there, sorry about that. Can't divide by 0. So anytime you have a variable in the denominator, you have to look at that and say, well, okay, x could be anything. However, x minus 1 can't be 0. So be careful here. Just because x is in the denominator does not mean simply that x can't be 0. That's not what it says. What I'm saying is the denominator can't be 0. So if I set x minus 0 to not be 0, add 1 to both sides, I know that x can't be 1. So the domain of this is going to be everything except 1. Okay, so let's write that. The domain. It can be anything except 1. So it goes down to negative infinity. So it can go from negative infinity up to 1. But can it be 1? And the answer to that is no, it can't be 1. So I cannot put a bracket on this, because if I put a bracket on the 1, that means yes, it can be 1. But no, it can't be 1. But is that my entire domain? No, because the only thing it can't be is 1. So I'm going to put a union symbol here, looks like a U, 1 to infinity. So that is the way to write set notation, to basically just block out one number. X can be anything except 1, and that's how you write it in set notation, or interval notation. Well, what's the range? So I'm dividing by something. The top number is 5. You take that number 5, you can divide it by anything you want. I don't care if it's positive, I don't care if it's negative, I don't care. You can take the number 5, you can divide 5 by 10 billion. 5 divided by 10 billion is very, very, very small. 5 divided by negative 10 billion, very, 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 very small. But it doesn't quite get to 0. So the range is everything except 0. So the range is from negative infinity to 0, union 0 to infinity. And again, we use parentheses because it cannot equal 0, and this guy is in fact a function. Variations of the definition of a function. A function is a relation in which for each distinct value of the first component of the ordered pair, there's exactly one value of the second component. That's one definition. Another definition. A function is a set of ordered pairs in which no first component is repeated. Another definition. A function is a rule or correspondence that assigns exactly one range value to each distinct domain value. All three of those said the exact same thing, just worded differently. When a function f is defined with a rule or an equation using x and y for the independent and dependent variables, we say y is a function of x. To emphasize that y depends on x, we use the notation y equals f of x. So y and f of x are the exact same thing, and they can be interchanged for one another. That's called function notation. To express this and read f of x, you can read that as f of x or f at x. Most of the time, I'm probably going to say f of x. Let f of x equal negative x squared plus 5x minus 3 and g of x equals 2x plus 3. Find each of the following. Folks, all this is saying is change the x values. So notice that my function is f of x, and part A says f of 2. Okay? What that means is they changed the x to a 2. So because they changed the x to a 2, I'm going to change the x to a 2. Now, when you're plugging stuff in, I want you to notice that that x became a 2 and it's in parentheses. I'm going to go through and everywhere there's an x, I'm going to put parentheses. So I have negative, there's an x, so there's some parentheses, squared, plus 5, there's another x, so I'm going to put parentheses, minus 3. Now what goes in the parentheses? 2 goes in the parentheses. It's very important that you understand what is being raised to that power. Okay? So now we just follow order of operations. Order of operations says do exponents first, so here's a negative sign, I keep it. 2 squared is 4. Plus 5 times 2 is 10. Minus 3. Order of operations. Negative 4 plus 10 is 6. Minus 3. 6 minus 3 is 3. So the function evaluated at 2 is 3. Okay, part B. I want to evaluate the function f at q. Folks, all that means is we're going to replace the x's with q's. So, change colors just to keep it separate. F of q. I'm going to replace each x with a q. And since I can't do any math with that, I'm just going to change the letters. In this case, I won't necessarily use the parentheses. So there's negative, there's my x, I changed it to a q, squared plus 5, there's another x, change it to a q, minus 3, and I'm done with part B because I cannot combine any like terms there. Part C, g of a plus 1. That means, hey, we're now working with the g function. So I'm going to drop it down here so it has a little bit more room. So here's part C. So g of a plus 1. I'm going to take the g function, and anywhere I see an x, I change the x to an a plus 1. So 2 times x. But x is a plus 1 plus 3. And now, since I've got it plugged in, I can do some math. I must. I will distribute the 2. 2 times a is 2a. plus 2 plus that 3 that's going along for the ride. 2 plus 3 combines, 2a plus 5. So g of a plus 1 is equal to 2a plus 5. For each function, find f of 3. All right, so part A. Part A is given to me as function notation. I want to change x to 3, so f of 3 is equal to 3. There's an x, change that to a 3. Notice it's in parentheses. Minus 7. 3 times 3 is 9. Minus 7, which is 2. So f of 3 equals 2. Part B, find f of 3. So f of 3, remember that right there? That's my x value. So I start looking at this guy. I'm looking for an x value, oops, there it is, of 3. So that right there is my, my 3. So for part B, f of 3 is 1. When I plug a 3 in, the 1 is my output. Part C, I have my domain on the left side and my range on the right side. I want to know what f of 3 is. So f of 3, I look through my domain, I see a 3. I see it maps to 5. So for part C, f of 3 equals 5. And part D, if this line happens to be my function, whatever it is, and it doesn't matter what the function is, y is f of x, I want to know what is f of 3. So I go on my x-axis, 1, 2, 3 is right here, and I go up to find that value. So f of 3 is 4. Finding an expression for f of x, consider an equation involving x and y. Assume that y can be expressed as a function of f of x. To find an expression for f of x, use the following steps. Solve the equation for y. Replace y with f of x. Assume that y is a function of x. Rewrite each equation using function notation. Then find f of negative 2 and f of p. So part A. First thing I need to do is get y by itself, and that's already been done for us. And since y is by itself, y is the same thing as f of x, so I could rewrite this as f of x equals x squared plus 1. It says then find f of negative 2 and f of p. All right, so let's do f of negative 2. I'm going to replace x with negative 2. Negative 2 squared, that's negative 2 times negative 2, which is 4. So f of negative 2 is 5. F of p, well, all I'm going to do is replace the x with a p, and there's no math that I can do with that, so I'm just going to change the x's to p's and get p squared plus 1. And I can't do anything with that. Part B, the first thing I need to do is get y by itself. So to get y by itself, the first thing I need to do is subtract x from both sides. By subtracting x from both sides, I get negative 4y equals negative x plus 5. To get y by itself, I'm going to divide every single term by negative 4. So divide that by negative 4, divide this term by negative 4, divide this term by negative 4. I get y equals, okay, so there I've got a negative 1 divided by negative 4. That would be a positive 1/4. And plus 5 divided by negative 4, that would be, don't forget my x there, and that would be a negative 5/4. And now that y is by itself, I'll do my two functions. Let's do, so we have f of x equals 1/4 x minus 5/4. What is f of negative 2? That would be 1/4 times negative 2 minus 5/4. 1/4 times negative 2 is negative 2/4. The board doesn't like writing on this side. I'm really sorry, folks. Minus 5/4. And negative 2/4 minus 5/4, that's negative 7/4. So f of negative 2 is negative 7/4. And to plug the p in, again, there's not going to be any math that I can do with that, so I'm just going to write it down. F of p equals, I'm changing all of my x's to p's, 1/4 p minus 5/4. And again, there's nothing that I can do with that, so I'm just going to leave it right there. Increasing, decreasing, and constant functions. Informally speaking, a function increases over an interval if the domain of its graph rises from left to right. So remember, in the United States, we read from left to right. So if a graph is going up, it's increasing. If it's going down, it's decreasing. And I don't care if it's going down steep or real slow, okay? Or maybe it's going down fast and slowing down, okay? So this graph here, that would be decreasing. If it's constant, it's flat. All right? I mean, that's as simple as it is. Increasing, it's going up. Decreasing, it's going down. Constant, where it's flat. The interval refers to the x values. So don't talk about y's when you're telling me about increasing or decreasing. I'm talking about as we read from left to right, when is the graph increasing? As we read from left to right, when is the graph decreasing? As we read from left to right, when is the graph constant? Here's the formal definition. And I really don't want to spend a whole lot of time going over that, but that's, if you're going on in advanced math, this is the kind of nomenclature you're going to be seeing, whether it's increasing or decreasing. Using the graph below, determine the intervals in which it is increasing, decreasing, or constant. Okay, so this graph here, I do want to point out the arrows, okay? So this graph, if I was going to read it backwards to the left, as I'm going to the left, that graph is going up, 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 and left, 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 okay? So at negative infinity, it is so far to the left and so far up, it's way up there. Now, let's start reading to the right. As we're moving to the right, this graph is coming down, 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 down. This graph is decreasing, 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 decreasing until it gets to that point. Okay? So this graph is decreasing. Where did that decreasing start? Well, it started when the graph started. The graph started at negative infinity. Comma. When did it stop decreasing? It's decreasing, 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 and then all of a sudden, at negative 2, at the x value of negative 2, it quit decreasing. Now, when you're giving me intervals of increasing or decreasing, pretty much you want to stay with parentheses, okay? So, because this graph, we don't know where negative infinity was, and it was decreasing until it reached the x value of negative 2, but instantaneously at negative 2, it quit decreasing, and this graph starts going up again. or up initially, because it was never going up to begin with. Okay, so you can't tell me that a graph is decreasing at -2 and increasing at -2. That just doesn't make sense. So let's just keep reading across this graph. From -infinity to -2, it was decreasing. And then the instant it got to -2, the graph starts going up. So now it's increasing. And that increasing started at -2. Again, we're only talking about the x values. So it's going up, 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 and all of a sudden, boom, it stopped going up. Where did it stop going up? Well, it stopped going up at 1. So it quit increasing at 1. Because the instant that graph, the x value, as soon as it hit 1, it became flat. And it goes flat forever. So it becomes constant. So this graph is constant from 1 to forever, infinity. The graph shows the relationship between the number of gallons G of water in a small swimming pool and the time in hours T. By looking at the graph, we can answer questions about the water level in the pool at various times. For example, at time 0, the pool is empty. The water level then increases, stays constant for a while, decreases, and then becomes constant again. So the water, it's empty. Over time, it's filling up. It stays the same for a while. Then maybe we let some water out, and then it stayed the same for a while. So from 0, it was increasing to this point here. Then it was constant. Then it's decreasing, and then it's constant again. What is the maximum number of gallons of water in the pool? Well, the y-axis represents gallons, and the highest this graph gets to is 3,000. So the maximum number of gallons in the pool is 3,000. When is the maximum water level first reached? Well, at time 0, there's no water in the pool. And then over time, it's increasing, increasing, and then finally it hits 3,000 at 25 hours. So it took 25 hours to fill that pool up to 3,000 gallons. Part B. For how long is the water level increasing, decreasing, and constant? Okay, so increasing. There's only one section of the graph when it's increasing. And so the increasing is 25 hours. Decreasing. Well, the decreasing section happens from here to here. So the decreasing goes from 50 to 75. Well, that right there, from 50 to 75, that's 25 hours. Constant. Well, constant is where it's flat. So it's flat from 25 to 50, so that's 25 hours there. And then from 75 to 100, it's also constant, so that's another 25 hours. So the total amount of time the water is at a constant level, 25 and 25, that would be 50 hours. How many gallons of water are in the pool after 90 hours? So 90 hours, 75. 90 hours is somewhere between there. So exactly where 90 is, I don't know. But since it's constant from 75 to 100, I know that from 75 to 100, we're setting at 2,000 gallons. So 2,000 gallons. Describe a series of events that could account for the water level change shown in the graph. I did that kind of a while ago when I was kind of looking at the graph. We filled it up, it stayed the same. We drained it, it stayed the same. And so that's one explanation. I'll give you the exact text from the book. It says the pool is empty at the beginning and then is filled to a level of 3,000 gallons during the first 25 hours. For the next 25 hours, the water level then remains the same. At 50 hours, the pool starts to be drained, and this draining lasts for 25 hours until only 2,000 gallons remains. For the next 25 hours, the water level is unchanged. All right, guys, I hope that helps you with section 2.3 functions and relations, and you're able to determine the difference between the two. Reach out if you have any questions. Be happy to help you. And y'all have a great day.